All right, I guess I'll get started here. Hello, everyone. Thanks for coming to my talk. Really quickly about me. My name is David Nicponski. I've been in functional programming professionally for the last 5 years or so, and was doing object-oriented imperative programming for about 15 years prior to that in industry. Did a bunch of stuff. None of that actually is particularly relevant to this talk. But feel free and get a hold of me later if you'd like to discuss any of it. Cool. So in this talk, I want to discuss interaction with databases and interacting with them in a way that encourages a rather functional approach leading to reusability and composition. I will cover a large range of topics, and the goal is not to make you an expert in any of the topics, but rather to give you just enough visibility to kind of understand each of the pieces and maybe to be a little bit dangerous in some of them. Cool. I'll start with the standard, industry standard means of interacting with databases and why it kind of sucks. So SQL. SQL is a problem. That's why we can't have nice things. It's ubiquitous in industry as a means of accessing relational databases. But anybody who has spent extensive time using it has run into any number of problems or downsides to using it. First, SQL strings are non-compositional. You can't easily take multiple pieces, and squish them together in a simple way to produce the natural composite effect. Naive attempts at squishing the strings together lead to all kinds of problems, like deeply nested subqueries, or potentially other problems which I'll discuss momentarily. SQL itself is not a type-safe language. There's nothing that prevents you from expressing nonsensical operations, only to have them fail at runtime when you try and execute them on a database. A common means of dealing with the previous couple of problems is just to copy and paste existing queries that seem like they are mostly what you want and modify them slightly to achieve the effect that you desire. This has all the problems of copy-paste to code. It interferes with maintainability and makes it easy to lead to version drift when the underlying data representation changes and each of the copies or near copies needs to be updated. Careless copy and pasting of SQL queries is also notoriously leads to injection vulnerabilities. It makes it difficult or impossible to be able to properly do positional prepared parameters in many languages. So it can make it very easy to introduce SQL injection attacks, which are, of course, the #1 problem on the OWASP top 10 list for security vulnerabilities. That's a very common problem. In addition to the security issues, naive use of SQL can lead to unintentional performance problems, such as the infamous n+1 query problem. Does anybody here know what the n+1 query problem is? No, okay, there are very few. So this happens, the common case for this to happen would be if you're trying to get some data from the database to populate, for example, a table, and your first query is going to determine what are the rows that are in the table. And then you're going to take the results of this query, and then for each of those results, you're going to execute like a data fetch to get the rest of the contents of the row. So for n rows, you execute n+1 queries. This is actually really easy to do with plain SQL strings, and popular ORMs also make it very easy to do, where you first do an operation to try and, again, figure out what are the things you want to display, and then a sequence of other operations to kind of get the details for display or for use. Popular ORMs often provide kind of escape hatches where you can give hints to them to tell them ahead of time that you're going to be asking for more follow-up data and that it should prefetch this data for you. Cool. So those are some of the problems with SQL as text. Let's discuss Slick. Slick it stands for the Scala Language Integrated Connection Kit. It is a Scala-based database access library. It is a functional relational mapping library to kind of contrast it with the more traditional object relational mappings. We'll get into what that actually means. Slick it provides an embedded DSL, type-safe, type-check DSL for query statements, insertions, and deletions. And the general idea is like tables are conceptually a stream of results or rows, where rows are themselves product types of the individual columns. So like I said, Slick provides an embedded DSL. This lets you manipulate the conceptual streams of results. You can filter them, transform them, map them, combine them, zip them, merge them, everything using type-safe embedded DSL. The types are used to ensure that only sensible, meaningful operations are being constructed. For example, you can't accidentally multiply an integer in a string or do something else, or use a join, create a join across different tables where you provide like a non-Boolean predicate, a non-Boolean function, non-predicate function for the join criteria. These are things you can easily express in SQL and strings, and they'll just fail at runtime. Cool. The embedded DSL is a compile time construct. At runtime, it is used to construct an object graph that represents the computation AST that's being constructed. And the AST is then compiled, again at runtime, into SQL using a particular backing database and the associated flavor of SQL that's appropriate for that database. SQL is executed against the backing database, typically via a JDBC driver or something similar. And in theory, you get your future of sequence of results, which will eventually asynchronously, hopefully, have your result sets. There's also a streaming variant provided by Slick to avoid materializing massive result sets and let you kind of paginate through results. In theory, the DSL that Slick provides is very collections-like. So anyone familiar with the Scala collections library, one would hope that it would seem familiar and intuitive. In practice, it's not really the case. But let's take a look at a couple of examples of using Slick. First, these are examples that are mostly taken from the Slick documentation, more or less. This should look relatively intuitive to anybody familiar with the Scala collections library. Coffees is a table. Here we're filtering the table into results that have a price greater than, I guess, $8 a cup or something, and we're retrieving the name. Of note, like I said, it uses the collections-like syntax, so at least seems kind of familiar. The types of the contents of the query are these rep types, which I'll talk about more a little later. They're representational types that kind of stand in for values that exist on the database, but that have not been materialized locally. So they're used to kind of capture the operation that's being constructed. Another simple example. This is equivalent to just finding a particular row with a particular primary key. It should be pretty straightforward, even for people who aren't too familiar with Scala. This is a slightly more complex query, where we're trying to take maybe the second page of coffees and grab just the name and the price. So this has kind of pagination built into it, as well as row projection. So we're discarding the columns in each row that we don't actually care about, leaving ourselves just the name and the price. Does that make sense? Anybody confused on that so far? Great. Cool. So I'd like to go over a couple of the different components of using Slick. Specifically, what are the different types involved? How do they come into play? How do they interact? And they kind of layered, and we'll work our way from the outside in. The outermost layer is the Scala concurrent future, your favorite lawless monad and mine. Eventually, it will hopefully contain the results of your materialized query and let you asynchronously compose operations if you so desire to do this at the Scala future level. Composition can be done at this level. But it's kind of too powerful for what I want to talk about here. Composition at this level basically implies that you have completed fully one interaction with a database and you're doing something else. It may or may not involve a database. It could be an RPC to a different system, but you lose things like composition. You lose things like transactionality if you try and do composition at this layer. And Scala features are just terrible. Don't use them. The next layer in, we have the DBIO action. which is also a type alias to a DBIO. This is Slick's internal implementation of the free monad. It effectively expresses complete database interactions, approximately corresponding to 1 round trip apiece, although they can also be the composition of multiple round trips. If you execute one of these on a database driver, you'll get back the future that we just looked at. Compositionality can be done at this level, and it's very easy. This is a lawful monad, and so you can do things like flat map across the results. We'll see an example of that. But doing compositionality at this layer has the same problem as doing it in many ORMs. We're trying to do it by hand in SQL. It's very easy to get performance problems, very easy to fall into the n+1 problem, which we'll see that. In some cases, it is actually required. If the thing you're trying to accomplish actually does require multiple distinct statements in sequence, even as part of a transaction, you have to do composition here. An example would be if you're trying to insert data into multiple tables as part of a single transaction. You can't do that with a single statement. One thing of interest, we noticed the DBIO action are blah blah. Those blahs are actually kind of interesting. Slick tracks at the type level using phantom types details about the nature of what you're trying to accomplish. So it can track the difference between read-only statements or queries and read-write mutations. And then you can basically make use of this to partition your queries and send the read-write ones to a current leader, and then send read-only to some standby replicas. Very interesting. And now we get into some of the more interesting types in Slick. The query type. The query type is not a monad, even though it exposes map and flat map. That's the first thing I want you to know. It contains a description of a computation and the computation's result set in type. The computation is a partially or completely constructed computation, but additional computation can kind of be tacked onto it. The semantics of your computation are eventually going to be reified into an AST when a value of this type is evaluated at runtime. I'll draw your attention to this inner type, rep of R. We'll come back to that. The reified operations that are eventually built into the AST can be used to produce select queries, insert, data inserts, delete statements, etc. In the insert case, the result type effectively will correspond to a projection of columns into which we want to insert data. In the delete case, the result set, like the row set, is going to correspond to the rows we want to remove from whatever table we're dealing with. And in the query case, as we saw in the prior example, it kind of corresponds to what we want to select in the select case. This is the type we saw inside the query. I mentioned before, there are these notion of representational types. These are types that are kind of stand-ins locally for values that exist conceptually in the database. A rep of double lets me have access to database side operations on doubles, but I don't have the double value locally. This is a pretty easy thing for early Slick users or new Slick users to get confused about. But they basically are what are used to implement the type-safe DSL to make sure you're only doing sensible operations on types that support them. Oh, that's wonderful. Yeah. Specifically, you don't have a foo locally in your Scala land. Great. So one of the goals of functional programming is reusability and composition. We'd like to have this when interacting with databases as well. We want to build correct solutions to complex problems by piecing together simple solutions of simple problems. When we do this, we want to have confidence that the results make sense, that we can reason about them, and that they have the intended effect. As I mentioned, in the Slick simple composition, you kind of pushed toward the DBIO level to do this. It's a monad. It makes it very easy for functional programmers to compose actions together. But as I mentioned before, it's kind of the wrong level for this to be done at. because again, DBIO actions correspond to approximately complete round trips of the database. And doing composition at this level is basically sequentially ordering database round trips. And so here's an example of composition at the DBIO level. You can see here we're first getting, oh, that's not what I was trying to do. Okay. Here. First we are creating a DBIO action that's, for some reason, gathering a list of primary keys of coffees that we want to display. And then we're kind of flat mapping that over the result set, getting new DBIOs to gather details that we want to display. For example, the name. This is a very kind of contrived example, but this is a pattern that you could see quite often if you do this naively. This will do many, many, many queries, n+1 queries to display n objects. Cool. So to get a better handle on composition and reuse, I want to take a brief detour to talk about something called Operads. Recently, if you've been to FP conferences or watched FP videos, categorical wiring diagrams have become very popular in applied category theory. Operads are kind of a generalization of the algebraic structure of operations in symmetric monoidal categories, and provide a convenient way to kind of visualize what's happening and visualize data flow through this context. I'm not going to go into what all that means, other than operads are kind of a generalization that's useful for us. Specifically, they embody composable abstract operations that have inputs and outputs. They come equipped with rules for what the types of inputs and outputs are. They have rules for how to combine the inputs into outputs algebraically, and rules for how data flows through the composite system in aggregate. And if this sounds like kind of what we want when piecing together database interactions, you're absolutely right. It's exactly what we want. You can think of operads as kind of like Legos or the old Connects if you're my age, where large structures are built out of smaller pieces, but there's a restriction that the pieces have to be kind of the right shape in order to click them together. Operads are kind of nice because they give rise to some slightly weird but kind of helpful wiring diagrams. So they're often visualized in this fashion. Operad is typically envisioned as like a circle that has holes inside the circle and wires extending out of the circle. The holes inside the circle correspond to inputs to the operad. The wires extending out of the circle are the outputs. This is an operad with 2 inputs and 4 outputs. Here's a couple more operads. You can see they each have like a distinct shape. Here's another one. This one has several inputs, each of different shapes. And serendipitously for us, the shapes of the inputs that it wants kind of correspond to the shapes of the outputs of the ones we just saw. Visually, that should hopefully be very suggestive of the idea that we can kind of snap them together and get something meaningful. And in fact, that's what happens. So each of the operads on the left fits nicely into a particular hole that's about the right shape on the right. And the end result is, I went the wrong way. The end result is this composite operad, which has our like 5 outputs and many, many inputs, but hopefully you all get the idea. It's kind of the natural notion of composition here. If you think of the wires as data flows, each of the operads is providing data from its piece of the construction of a query or a statement, and it's feeding it into something that's wanting that kind of information. Ideally, we want to be able to wire these together in a sensible way when dealing with database. With this model, operads can be used to kind of encode semantically meaningful chunks of operations, and then we just piece them together, connect the wires in a way that makes sense, and that has some meaning to us, and proceed. Cool. Of course, not everything, eventually you have to stop requiring inputs from other people. The individual tables in your database can be thought of as operads that take no inputs. They just provide their data as outputs. Similarly, literal values can be thought of as operads that provide outputs but no inputs. Tables can be thought of as operads that have outputs, one per column, or correspondingly as the product type of all their columns. Cool. Any questions on that so far? Everybody's fully with me, excellent. All right, so now I want to describe the general approach taken in Sloppy, which is an up-and-coming kind of newish library that's in codifying the techniques that we used at my last employer to kind of do this exact technique. So functionality, database functionality is encoded in polymorphic operads, which we call query transformers. I don't know if polymorphic operad is the right term, but I haven't found a better term to describe this. Cool. So the general idea is that these transformers are going to change queries into other queries. Transformers might need some kind of input values in order to work. These correspond to the inputs in the operads or the holes in the operads. Typically, these are a value from each row, although they could just be a literal value. Transformers know how to figure out what is the destination type for the query that they're producing. Typically, this is done by a type level function that maps the polymorphic input type into an output type. Yeah. Transformers can turn a query of type A into a query of type B, provided that they are given a query of type A and a way to extract some value of type E that they care about from the rows of the query of type A. That's a lot of kind of abstract stuff. Did it make sense, or should I repeat that? Yeah, everybody seems to have gotten that. Cool. In Scala, they kind of look like this. Query with its row type A and a way to extract E's that we care about from the A's will give you back a query of type B. If you don't know Scala and you know Haskell instead, kind of squint at it and pretend that the square brackets aren't there. And that's approximately, and that the double arrow is a single arrow, that's approximately what you get. An operad diagram world, this is kind of the operad shape of these generalized query transformers. They have inputs that take some arbitrary polymorphic type A, a way to get E's out of them that they care about, and we'll give you back a B. This is the most generalized form, though. There are some pretty common patterns that I found tend to occur repeatedly, and those seem to be much more useful in practice. So yeah, here's the most common one that I found. This is if you have a query that has some data in it, I will give you back a query with all of your same data and some more data that you are asking for. So it's kind of appends data onto each row. And this looks like this. It's the same as the previous one, except we're also giving you back the data that you started with. All right, so let's take a look at this in practice here. I started working on a library called Sloppy. Sloppy is the Slick Operads library. Caveats, don't use it in production. Although we did use this technique in production for many years at my last employer, it wasn't using this library. This library is a new thing I've just started working on. I haven't yet published it to any place where it would be easily usable. Cool, let's see if I can get to the demo here. Is this text big enough to read for everybody here? Yeah, good, okay, great. So this is a very, very simplistic example just to kind of show you the surface of Sloppy here. Feel free to yell at me afterwards if it's too simple. But the basic idea is I have a very simple model of a social network. It just has people and then relationships between people. The relationships are tagged with a particular attribute, so you can have friend or mother, son, etc. These are some kind of domain model objects in Scala to represent those. These are the representational types that correspond to the product types that I just described. If you recall, that's a thing that Slick requires. Ignore the man behind the curtain in the bottom there. I mentioned that query transformers implement a type-level function from an arbitrary input query type into the produced output query type. That's what this destination shape is. Takes in a lifted and non-lifted type, RA and A, gives you back a new type, V and RV and V, which are the lifted and non-lifted types respectively. Cool. Query with extractor. This is a here's the important part here, is it basically wraps a query in a way to get values out of each row in the query, or to produce literal constant values for use. This code here is actually in the library, so it's not what you would be writing or having to interact with, but this will show you some of the types involved. This is the most generalized form of the query, the full query transformer. It can transform queries of an arbitrary type that contain RA and A, which are the polymorphic contents. As long as we are given an RE and an E, we will compute the shape, the output shape of the query we're going to produce. And so concrete implementations must implement this transform2 function, which takes in the query with extractor that knows how to give you the RE and E that you need for your input, and you produce the query that has the results of the type level function. For those who aren't too familiar with Scala, this is how the type level function kind of looks. These are the output types. I mentioned there were a couple of common shapes. This was the appender. This is just one where the type level function is simply kind of appending by a tuple append of the value that we produce, and it's passing through the input value as the left side of the tuple. Another common shape we found is one that doesn't change the shape of the input at all. This, for example, would be is commonly used if you just want to restrict the contents of the result set. Let's say you want to filter out so that only people whose age is a prime number are in the result set. You don't want to change the contents of the data. It's a very common shape we found. Cool. So I'll show you a couple of examples in approximately increasing order of complexity. Feel free to stop me if any of this doesn't make sense or if you have any questions about it. First example, this is basically just raw Slick. This is showing how computations on the database can be built up in the normal Slick fashion. The first is producing a query that just does a projection into a particular set of columns from the table. And then we further refine the queries by filtering for particular users in the query. We can compose these together, compose the result sets of these together. And this kind of works how one might expect. Oh, yeah, okay. So this works how we expect. We find the two people. Our composite query works and finds both people. Cool. So now I'm going to get into actual uses of Sloppy to be able to manipulate the queries in a relatively generic fashion. So if we recall, ARIA is a query. It has the effect of only returning a single row, which is the user ARIA. But there's no reason that we have to use that particular query. The whole point of these is we could use this on any query for which we could extract things we care about, in this case, the individual user's names. So we provide a way to get the values that we care about, which in this case is done by using the name present in the result set of the ARIA query. We can append the stuff that this appender knows how to produce. Let me take a look at this appender here. Okay, add friend 0. This is an appender that, given a name, knows how to attach a linked person. If you recall, this is the model object that I showed you at the beginning. It's just a new person with the relationship by which we're linked. And this has as implementation, as I mentioned, we just have to implement the append to method. It looks, anyone who has seen Slick, this is not too atypical. The main thing I wanted to show here is that this is still not as generalized as it could be, because this is strictly looking for people with a friend type relationship. And when we find people with a friend type relationship, we're strictly adding that user to them. Like both of those could be abstracted and made this more reusable and more composable. But the general idea is this is going to take anything where we can get a user's name, and it's going to expand it into the user's name and all the user's friends. Yeah, and this worked. I'll note that my data set for Game of Thrones is inexhaustive. And probably doesn't take into account the last season, so there's no spoilers there. Cool, so I mentioned a couple of ways that add friends appender could be generalized, that we don't have to restrict ourselves just to that relationship type or to that particular type of table to join against. We could take both of those as parameters, for instance, which is what this next implementation does. This is adding person is basically the same as the add friend 0 we just saw, except it's parameterized on both of those two things that I described before. We can take an arbitrary number of relationships that we care about. We can take a source of user-like things that we want to join against. It could be another query, it could be some other filtered thing. And otherwise, the implementation should look basically the same. Okay. In this case, I didn't specify a particular linked relationship type, so this was all relationship types, including the family members. And I could restrict it just to particular relationship types if I so desired. I'll spare you that one in the interest of time. Now we get to kind of the interesting part, I think, which is that we can chain these together and compose the effects of these. So if we have an appender, which corresponds to siblings, appender that corresponds to parents, add linked it was just like exhaustively expand across my relationships. We can compose the effects of adding my parents with adding their relationships. So this is going to be friends of their parents, basically. Yeah, so Arya's mother is Catelyn, Catelyn's friends and relationships are all there. So that was done by chaining together these appenders, but we can also compose the appenders directly. So for example, parents again was an appender without a query it's operating on. So we could just directly compose that appender with the appender we just used, the exhaustively expand my relationships. And that'll work and compile and produce exactly the same result set that we just saw. Again, I'll spare you that one. Yeah, and this can be done, kind of ad nauseum. So we can get mothers, spouses, mothers-in-laws by kind of composing those, siblings, friends, mothers-in-laws by composing all of the things we've seen so far. And it kind of makes sense. Each of them provide a little piece of semantic meaning to the composed query, and the meaning of the composition is the composition of the meaning. So it's exactly what you would kind of want them to be. Cool. And I guess one more example I have here for composing these transformers. So we can have a transformer that is using the filter example, so it's just reducing the result sets, but not changing the data. So the only popular filter This is a query contents filter. It doesn't change the shape of the input query. This is what I described as the filters. All it needs is it needs about names, and it's going to remove from the result set anybody who's not particularly popular, and parameterized on some threshold of popularity. In this case, the threshold is 4 by default. And so popular people are just users who are filtered to being popular, but we can also compose that with itself, so we can find people who are popular and friends with popular people. Right, so this is popular people, and then who are friends with popular people. And this, I guess we could call them like the social elite in Game of Thrones. This is a symmetric relationship, so you would expect only the popular people who are friends with people in the popular people list would be in the final result set. And sure enough, that's what we see. So I put this together, actually, this example together a couple weeks ago, back when it was still approaching Mother's Day. But this is, you can kind of glance over this and see, we're just composing these appenders and filters in a way that will let us figure out who should be saying Happy Mother's Day to whom. And this is people who have living mothers in the social graph, or who are married to people who have living mothers in the social graph. And that works just fine. One thing I want to show you also is like, what does the generated SQL look like? Because that's not always so pretty. So yeah, the composition of these things work. All the men should be saying Happy Mother's Day to their mothers and mothers-in-laws. Right? The SQL I wanted to just point out, anybody who's had to deal with assembler, like this looks like assembler, right? As a result of a compiler acting on an input language and producing something low level. Cool. With that, let's go back to slides.
That was all one big query.
Yeah, that was one big query. So one of the properties of using this approach is that you are producing a single query. So like by definition, you can't get the n+1 problem. You can achieve the same effects of getting all the data by composing these pieces together, but it'll be compiled into one large query. Cool. As I mentioned, this library hasn't been used in production yet, but the techniques here were used pretty extensively at my last employer. Examples were, it turns out, for better or for worse, for legacy reasons, a lot of the data was stored effectively in RDF triples, despite being in a relational database. So we implemented a very generic implementation of the RDF system in using these kind of techniques. A single abstract implementation that made sure to use like efficient joins and all the appropriate indices, and then a couple of specialized wrappers around these. And they basically just did type specializations to restrict to certain portions of the application functionality, but all had a single implementation. This amounted to maybe 10,000 lines of code total, and replaced about 300,000 lines of PHP. Another example, the entire entitlements and permission system at Seamless Docs was based upon this. Really, the entitlements required that you know what is the type of domain object that we're retrieving from the database, who is the current user, and that was it. And given that, we could, regardless of what other data was in the query, we could remove from the query results stuff that the user wasn't able to see. Again, this had basically was single implementation per kind of class of domain objects, and that was it. Simple, fast, and well tested. Less frequently, but still as useful, was for data migrations in response to schema updates. This was very useful because we could have like the canonical implementation to extract data from wherever it currently lived, even if that was like implicit and built into the relation somehow. Could make this explicit in the results set of a partially constructed query, which could then be forked and the data could be sent off to do inserts into other tables where needed. This we didn't do, but I think is a very natural fit. GraphQL, you often want to expose some kind of virtual schema to the consumers of your GraphQL API. The virtual schema in examples often maps one-to-one into your underlying relational database, but that doesn't really make sense in the real world. So if you want to be able to map GraphQL queries into kind of the more complex underlying relational queries needed to power them, I think this would make a lot of sense. I'll go kind of fast through here. So not everything with Slick is as nice as one might hope. There are some problems. The first is that Slick relies on shapes everywhere. Shapes witness the correspondence between representational types and materialized Scala types. Slick does a lot of amazing and complicated implicit magic to try and make this automatic, and it doesn't always work, and it's not always obvious how to fix it if it doesn't work. Some things Slick does, in my opinion, makes the wrong behavior easy and the right behavior hard. For example, it kind of encourages composition at DBIO level, but as we saw before, this leads to performance problems and excessive round trips. I mentioned the query type is not a monad. It makes you think it is, and if you try and use it as a monad, you will find yourself with some runtime heartache and probably runtime failures. It also is missing common table expression support and common subexpression elimination, both of which would be very, very useful for this. A lot of complexity in the Slick library is based on the idea that you want to be able to support some kind of behavior patterns, which in real world nobody ever does. They make it possible in theory to be able to substitute different backing database drivers, but nobody ever tries it. Nobody migrates from Postgres to Oracle in the real world, but the implementation complexity is there to support it. IntelliJ it is not reflective of the real world when it comes to Scala, and this is exacerbated with complex libraries like Slick. Compilation to SQL can be slow, and by slow I don't mean it's that slow, but you don't want it on the user hop path. So you want to be able to precompile and cache these, and in fact, Sloppy provides a way to do that. So PK is a precompiled query, doesn't suffer the compilation penalty on each use. Cool. So in summary, Slick gives you an embedded type-safe DSL to express safer database operations. With careful techniques, the operations can be composed and reused in meaningful ways. Sloppy gives you the types and tools necessary to be able to do that and do it in a less painful way. And the same techniques that I use in Sloppy can actually be applied for other systems. For example, there are Haskell DB libraries for which this would very naturally be applicable. Basically, any system where you're building up a computation in steps, you should be able to use this kind of higher order transformer approach to grab your usable pieces. And the library is still under design. Please feel free and help or come talk to me. Thanks. Looks like we might have time for a question or two. There's also extra material in the slides if you want to do any additional reading. Questions? Yes. Either one.
So how do you switch out different JDBC implementations? Which level does that happen at? Or do you have to significantly change things if you want to move your app to different databases?
That's a great question. So the question was, what do you have to do if you want to switch out different database, underlying databases? If you're only using Slick at a very simple level and you're not doing anything that is custom to the database that you're currently using, then in theory it's pretty straightforward. One of the types I didn't mention is the actual driver. The driver is a subtype of a database driver or database profile that is specialized for your backing database. These drivers and driver profiles can kind of introduce additional functionality or additional DSL support that is only possible for that database. And as long as you're not using that, then you can just substitute drivers. In my experience, we were using Postgres, and I think we lasted about maybe 2 months before venturing out of the raw SQL and into the Postgres flavor, just because it was too convenient not to do so. Yes, sir.
When using this, do you end up using the same approach to creating indexes and optimization that you would using raw SQL or an ORM, or do you ever find yourself needing different types of indexes?
So the question was, do you find yourself creating similar types of indexes using this approach as you would if you were just doing it kind of by hand or using an ORM? That's a great question. I don't know the answer to that because I don't have a lot of experience trying to do performance tuning either via string SQL or ORMs. The general approach that I took here was there were a couple of indexes in most tables where it was obvious that these should exist because expected query patterns, we're likely to have this kind of data. But then once you have the general like composed query, you can dump the SQL, run it into an explain on your database, and see like what does the query plan look like. If you see linear scans through the tables, then you better introduce an index, or you better like reformulate it in such a way that you can use an index. Answer your question?
Right. I was just wondering if the way it generates them is so ad hoc that you want to explain might not be represented for those that you might do in a different situation.
Gotcha. So the question was, does it generate them in an ad hoc fashion that might make the explains non-representative? No, the thing that made explains less representative would be to use a much smaller subset of data. So if you have like a non-production database that has 1% of your data and you do an explain there, you might see a very different plan. But the queries are generated deterministically. Okay, so one more question over here. Yes, sir.
How much query complexity does sloppy add over creating hand-creating the best query agents like ORMs?
So the question is, how much complexity does sloppy add compared to hand creating the best query in either in Slick or in SQL? Yeah, that's a great question. Compared to the best query in Slick, I think it's at least comparable. I don't think it's any worse, unless your query transformers are implemented in a particularly poor way. I mean, you can always implement, you could do some roundabout set of joins that are unnecessary, but whatever you would have implemented, let's say your query naturally is do thing A, then B, then C, and you're trying to pull part C out. As long as you're doing roughly the same set of operations in part C in your query transformer, it's going to do the same thing when you piece them back together. In terms of comparing this to SQL, in raw SQL, you can sometimes make use of common table expressions in a way that would be more efficient than you can do in Slick, but that's true whether you use sloppy or not, just because Slick doesn't support CTEs. I do find that it can potentially be exacerbated using this approach, because you might have like a prequel or prelude set of operations that you're doing and then using this multiple times in a query, that then all the data then gets kind of pieced back together. And with a CTE, you could do that once. And in this case, the query planner may or may not be smart enough to figure out that it can be done once and then reused. That's also an issue in Slick itself, though. It's an outstanding, for like 4 years or something, an outstanding feature request to add that. All right, I think we're out of time. Thank you, guys.